In this work, we present a system which determines the optimal flow for large crowds of agents in a scene, such that they cooperate to reach a given goal or set of goals in the shortest time. Our system plans the motions for crowds of agents moving from a set of start points to a set of endpoints. We start by computing a harmonic field across the environment, with its values set to 0 at the start points and 1 at the endpoints. As it is affected by obstacles in the environment, this field gives a good representation of the available space. It also gives a smooth transfer between the start and endpoints which, by following the gradient, provide smooth, efficient paths for agents to follow, called guidelines. By separating the field into regions containing certain ranges of values, we can produce a read graph. The connected read graph gives a good representation of the topology of the space, including any obstacles, which we can use to plan out the motion of the agents. In order to produce this plan, we must first compute the capacity of each of the edges in the read graph. We do this using the length of the ISO flow lines, which run perpendicular to the gradient of the harmonic field. This gives us capacities for the edges of the graph and allows us to find the maximum flow from the set of start points to the set of endpoints. This in turn tells us how many agents can fit in the scene and, in the case when the scene is filled to capacity, how many agents will be moving along each edge. Here we show our system filling the scene. The values given by the maximum flow are followed to dictate how many agents should go where, and each group of agents is following the flow lines appropriate to the route they are taking. Here, the system has planned the motion for a small village scene with 7 obstacles and over 300 agents. The system can also utilize multiple start and end points, as seen in this simulation of an evacuation scenario. Here, the blue cylinders show stairs arriving on the ground floor of a building, with red cylinders representing the exits from that building. Again, the agents are seen to coordinate their motions as though in a well-rehearsed fire drill. Due to the topological nature of our system's motion planning, it is possible to scale up the plans significantly with no further computation. In this example, there are over 70,000 agents in total. Here, a comparison can be seen between our system, above, and the continuum crowd system, down below. Continuum crowds agents all focus on the shortest route with no consideration for cooperation. This leads to a large amount of congestion arising in the centre of the scene. We have created tools that allow a user to use the values our system computes to determine how congested they would like the produced scene to be. Here, a value of 1 represents the known capacity of a scene as found by our system. We cycle through a range of values to demonstrate how the scene is affected as this value changes. Additionally, we also allow a user to specify how much they would like the agents to cooperate. With less cooperation, agents are more greedy and switch to picking shorter routes to the goal, even when this will be slower for the crowd as a whole.